Hello students and welcome to the lecture. So students, as we know that we are covering the light, right? And so far we have done with the part 3 or 3 parts you can say. Basically, in this lecture, what we are going to start is light part 4. Okay? I hope you have revised the previous 3 parts in the well enough manner, especially the part 3. Because this part 4, is going to be related with part 3. In the previous lecture also, I had reminded you one thing. All these parts are interconnected with each other. This part is interconnected with them, and the upcoming parts will also interconnected with this part and those previous parts. Okay? Why I'm saying that the part 3 is to be revised first before watching this lecture, because here when I will show you the topics that we are going to discuss, then you will figure it out that why I have told this. But here it's my duty to remind you, kindly revise the facts and figures that all we have discussed in one lecture before you make yourself available for the next lecture. It's for your own benefit. Okay, so here this is the index. Here we are going to talk about the some effects of refraction, critical angle, factors affecting the critical angle, total internal reflection, condition for total internal reflection, some examples of total internal reflection, prism, refraction or bending of light through a prism, factors affecting the angle of deviation. Okay, so if you look at here, reflection, what you are getting. In the previous lecture, we had start the discussion over the refraction, right? Even we had seen several points that are very important from the point of view of understanding the refraction. So here again we are going to talk about the same topic further. That's why I told you, if you have not revised the previous lecture in the well enough manner, you won't be able to grasp the facts and figures that we are going to unfold here. So we will talk about some effects of refraction, critical angle, factors affecting the critical angle, total internal reflection, conditions for total internal reflection, some examples of total internal reflection, prism, refraction or bending of light through a prism, factors affecting the angle of deviation. So these areas are going to be the discussion points for us for that particular lecture. Sorry, for this particular lecture. But before starting of the actual lecture, like as usual, we have the small disclaimer over here that we are required to understand before we proceed further. So a disclaimer goes like this. The images used in a slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this deck and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the images. Now, let's begin with the topic of some effects of refraction. So, we know what do we mean by the refraction or whatever we mean when we say refraction. When the light is coming from lighter medium to any denser medium, or you can say from denser to lighter, or you can say simple in a simple terms, one transparent medium to another transparent medium. Whenever the light is coming like this, one transparent medium to another transparent medium, that is the case of refraction, right? So here, why the refraction phenomena happens? Because the speed and wavelength of light changes, but the frequency or color of the light do not change while passing from the one medium to another medium. So that's why we often notice the phenomena of refraction. So here we are going to talk about that what are the daily effects that we're seeing in our daily lives, and these effects are actually belong to the phenomenon of refraction of light. So the first that you can see, a stick or a pencil dipped in a water appears to be short and bent at the surface of water. So like this you can say, if you having a transparent glass of water and you put a pencil in it. So two things will happen. First, the pencil will appear as bending. Second, if you look at the pencil from the top surface, you will find out that the pencil in appearance is looking shorter than it's actually. Okay. Second effect, a coin capped in a vessel and not visible from the edge of the vessel could be viewed by pouring water in the vessel. For example, suppose you have put a coin there and this coin is not visible to you when you are looking at it from here. But then if you pour water in it, then you can see the coin will become visible to you. Why? Because of the refraction of light. Even you could try it today. Just take a glass water. Okay, sorry, the glass. Okay, and transparent glass it should be. Just put a 1 rupee coin at the bottom of that glass and try to see it by the aging. You won't be able to see the coin clearly. But if you pour a water in that particular glass, you will find out the glass will, the coin will become visible to you. Why it is happening? Because of the refraction. A print appears to be raised when a glass block is placed over it. So you can say at the homes, not at the homes, sorry, at the offices, we generally have the uh, glass holders, okay, to hold the paper. Or often we call them as a table holder or paper holders. Okay, so if you have any paper holder that is transparent, just do one thing: put a paper on the table and place that particular glass holder over it. That must be a transparent. You will find out that the print on the paper will be appear here at the surface, but the print is here on this paper, but it will appear at the surface because of the refraction. Okay. Multiple images in a thick plane mirror. The twinkling of star, this is the phenomenon that we have often seen in our childhoods. Like in the childhoods, most of you, even some of you today, look at the sky during the nights and you will find out that the stars are actually twinkling, right? You'll find out they are blinking. How? Why? Because of the refraction. The light of the star before reaching you is actually going passing through many mediums. That's why its speed is continuously changing, wavelength is continuously changing, but the frequency is not. So that's why it is actually appears to be twinkling because of the phenomenon of refraction, because the light is passing through multiple mediums before reaching your eye. The twinkling of a star is due to refraction of light from the star at successive layers of increasing refractive index towards the Earth. Sun is seen before sunrise or after sunset, even when it is below the horizon. So you can say, if this is a person standing, this is the horizon. Okay, so he could still see the sun before the sunrise and after the sunset, even when the sun is here. Why? Because the light of sun is reaching your eye while passing through so many air layers of increasing refractive indexes. So that's why it is appearing you that the sun is still out there, but the sun is not. Oval shape of sun in the morning and evening. Like you can say in the morning and evening, you will find out that the sun shape is not as usual. It is oval or bulge like this one. It is also because of the refraction. Got it? Here you can say also like this is the star actually. Okay, and you will see the star here. Why? Because once the light started towards your eye, it's going through so many mediums, so many successive air layers, and then it's reaching you. So that's why the actual position and the apparent position of star appears different. It is also related with the refraction. Now, After finishing the some effects of refraction, let's have a look over the critical angle. What do we mean by this? That's the main point. So when a ray of light passes from a denser to a rarer medium in such a way that the angle of refraction becomes 90 degree, the corresponding angle of incident in the denser medium is called the critical angle for the given pair of media. For example, this is the light coming from denser medium to a rare medium. We know it will be reflected. Okay, so this is the angle I, the angle of incidence. Okay, this is angle R, the angle of refraction. So generally what is happen with us as per the Smith's laws, the angle I will always be equal to angle R, right? This is the normal case. But here we are not taking this normal case into the consideration, but we are saying that in respect to the angle I, the angle R is 90 degree. Okay, so here what is the case? When a ray of light passes through denser to a rare medium and the angle of incident is this, but the angle of refraction is 90, then it is called the critical angle for the given pair of media. Okay, in other words, critical angle is the angle of incidence in the denser medium corresponding to which the angle of reflection in the rare medium is 90 degree. So what we could say that whenever this condition will happen, angle R would be 90 degrees. So always the angle I, that will always be a critical angle to the rare medium. Okay, if in correspondence to angle I, the angle R becomes 90 degrees, so angle I will always be a critical angle for the rare medium or the opposite medium, or you can say for the given pair of medium. Whatever you want to call it, you can call it, it's your call. Relation between the critical angle and the refractive index. In figure, AO is incident ray from glass to air at an angle of incidence IC, critical angle, for which the angle of refraction is 90 degree. Okay. Now, let's move forward. Therefore, the refractive index of air with respect to glass is G mu A equals to sine IC by 90 degrees, sine 90 degree, or 8 mu A equals to sine IC. It is sine 90 degree equals to 1. But A mu G equals to 1 by G mu A. But A mu G equals to 1 by sine IC equals to cos sec IC. Or sine IC equals to 1 by AUG. Now what are the factors that affecting the critical angle? Okay, we know what do you mean by the critical angle. We have gone through it. Now it's a time to go through the factors that are actually affecting the critical angle. So the critical angle for a given pair of media actually depends on the color or wavelength of light. It is to be noted that the refractive index of a transparent medium is more for the violet light and less for the red light. Therefore, the critical angle for a pair of media is less minimum for the violet light and more maximum for the red light. So first factor that is actually going to affect the critical angle is your color or wavelength of light. Okay, so if we take the refractive index of a transparent medium, we could say for violet light it's more and for red light it's less. That's why the critical angle for a pair of media is less minimum for the violet light and more maximum for the red light. For a given light, it depends on the nature of pair of media. Lesser is the value of mu, greater will be the critical angle and vice versa. So if we take a given light, it actually depend upon the nature of pair of media, how the pair of media is. Denser to rare, rare to denser, whatever you can call it. So if the mu value is lesser, critical angle will be greater. If the mu value is more, critical angle will be low. So you can say mu is inversely proportional to the critical angle. If one rise up, another will go down. If One goes down, another will rise up. That's it. So keep this thing in your mind. So when a ray of light traveling in a denser medium is incident at the surface of a rare medium, such that the angle of incidence is greater than the critical angle for the pair of media, the ray is reflected back into the denser medium. Here you can see this is the denser medium, this is the rare medium. So what is written down here? When a light ray traveling in a denser medium incident at a surface of a rare medium, like this one, okay, such that the angle of incidence is greater than the critical angle for the pair of media. So this angle of incidence is actually greater than the critical angle for this particular situation. Then the ray is reflected back into the denser medium, like this. Ray is coming, hitting the surface. Angle of incident is greater than the critical angle, so it will be reflected back to the same denser medium. This phenomena is what we call total internal reflection. Now you can say there is a thing that we are required to understand why it is known as the total internal reflection. Why? Because it is the reflection of a light ray within the same medium. If the light ray is going like this, then it will not be a case of total internal reflection. Why? Because the incident ray is actually penetrating through this. Okay, but here you can say the incident ray come, hit, and again reflected to the same medium. It is not able to cross the boundaries of the medium of which it was previously held, right? So that's why it is the internal reflection or total internal reflection, because the light ray is not able to penetrate the medium in which it is flowing. Got it? Let's move forward. Now let's have a look over what are the conditions for total internal reflection. So there are mainly two necessary conditions for total internal reflection. First condition is light must travel from a denser to a rare medium. Okay, this is the foremost condition. We could not reverse it. Like rare to denser, it always must be a denser to a rare medium. That is the first condition. The angle of incident must be greater than the critical angle for the pair of media. So if the angle of incidence is equal or lower to the critical angle for the pair of media, the total internal reflection could not be possible. It could only be possible when the angle of incidence is greater than the critical angle for the pair of media. There is an important note. When total internal reflection occurs, the entire incident light, that is 100%, is actually reflected back into the denser medium. Whereas in ordinary reflection from a plane mirror, some light is refracted or observed, therefore reflection is partial. So if you talk about like what is the difference between the total internal reflection and a normal reflection, the difference is that this is the case for total internal reflection. This is the denser medium, this is the rare medium. The incident ray coming and reflected back. It is not penetrating, but in a normal scenario, in the normal reflection, this will happen, right? So you will say that the both cases are looking same, right? This is the total internal reflection because the light is reflected. This is also. So why we are saying this is normal reflection, this is total internal reflection? Because in such a case, some light is observed and some light actually penetrate the another medium. Okay, but in that case, entire 100% incident light will be reflected back. It will not able to penetrate the another medium. So that is the basic difference between the total internal reflection and the normal inflection. In the total internal reflection, 100% of light will be reflected back. In the normal, some light reflected back, some got absorbed, and some able to penetrate to the another medium. Okay. Now, critical angle for some substances in respect to the air. Why we take air? Because we think that the air is the lightest or rarest medium that we could have here on earth. Okay. Substance mu critical angle. For water, mu is 1.33. Critical angle 48 degree 55 minutes, or you can say 49 degree. Turpentine 1.47 42 degree 54 dash of minutes equals to 43 degree. Glass 1.5 mu 41 degree 48 dash of minutes equals to 42 degree. For pint glass 1.57 critical angle will be 39 degree and 30 degree equals to 39 degree. For non 2.41 mu critical angle will be 24 degree 30 dash of minutes equals to 24 degree. So this is the table that is for your just a knowledge. For water, mu is 1.33, critical angle 48 degree 55 49 degree. Turpentine, mu is 1.147 42 degree 54 43 degree. For glass, mu is 1.5 41 degree 48 42. For int glass, mu is 1.57 39 degree 30 39. For non, 2.41 mu is 24 degree 30 dash equals to 24 degree. Now, some examples of total internal reflection if we take them into the consideration. First is mirage in desert. Sometimes in desert, an inverted image of a tree is seen which gives a false impression of water under the tree. For example, if this is a desert, you are standing here, and if you look at this tree, so at quite distance you will find out that the inverted image of the tree will be appear here. So we often thought that there must be a water, okay, but the water is actually not there, and that is what we call as a mirage. This is called mirage, like the thing which is not happening. The cause of mirage is the total internal reflection of light. In the desert, the sand becomes very hot during the daytime and it rapidly heats the layer of air in its contact. For example, this is the sand. This is the layer of air in the contact of the sand. So in the daytime, this layer will become critically hot because of the contact of hot desert lies beyond it. Okay. Therefore, the layers of air near the ground becomes warmer and hence rare than the upper layers. In other words, the successive upper layers are denser than those below them. So, when a ray of light from the top of a tree travels from a denser to a rare layer, it bends away from the normal. As a result, at the surface of separation of successive layers, each time the angle of incidence increases and ultimately a stage is reached when the angle of incidence becomes greater than the critical angle between the two layers. At this stage, the ray of light in traveling from denser to a rare layer suffers to total internal reflection and got reflected back, as you can see in the figure. Okay. This reflected ray now travels from a rare to the denser layer, so it bends towards the normal at each reflection. On reaching the eye of the observer, an inverted image of the tree is seen. That's why the observer often get confused or becomes fooled that there must be a water there, but there is no water actually. Thus, it gives a false impression of pool of water in front of the tree. Sometimes mirage is also seen when driving on a hot, still summer day for the reason. Now, the second effect is looming of water. Sometimes in the very cold countries near the sea or in a sea region, inverted image of a distance object is seen. This is called looming of water. The reason of looming is the total internal reflection. In cold countries, the air layers near the ground being very cold are denser than the upper layers. So when a light rays from a ship or distance object traveling upward from the denser layer to the rare layer bend away from the normal due to the reflection at each layer, and ultimately a stage is reached when the angle of incident at a layer becomes greater than the critical angle. So they suffer total internal reflection and reach the eye of the observer, giving him a false impression of sea or other distance object as lying inverted in the sky. Shining of an empty test tube inside water like a mirror. If an empty test tube is kept in a beaker of water, its surface inside the water shines like a mirror. This is also due to the total internal reflection of light. Rays of light traveling from water to air at the surface test tube strike to an angle of incident which is greater than the critical angle for water air media, equals to 48 degree 45 dash or minutes. Therefore, they suffer the total internal reflection, as you can see figure in the eye. Thus, the surface of the test tube shines like a mirror. Shining of air bubble. An air bubble in water shines due to total internal reflection and its outer surface. Here, the light is propagating from denser medium to a rare medium, air, and angle I is greater than the theta c, 49 degree. So total internal reflection, which is here abbreviated as TIR, will take place at the surface of the bubble. Sparkling of diamond. The sparkling of diamond is due to the total internal reflection inside it. As refractive index of diamond is 2.5, so theta c equals to 24 degree. Now the cutting of diamond are such that angle of incidence is greater than the critical angle. So total internal reflection will take place again and again inside it. The light which beams out from a few places in some specific directions makes it sparkle. Recently developed synthetic rutile titanium dioxide displays even greater brilliance as for its mu equals to 2.9 and so theta c equals to 20 degree. Optical fiber. An optical fiber is a device which is based on total internal reflection by which a light signal could be transformed from one place to another with a negligible loss of energy. In it, light through multiple total internal reflection is propagated along the axis of a glass fiber of radius of few microns, nearly 10 power minus 4 centimeter, in which index of refraction of core mu1 equals to 1.7, greater than that of surrounding called cladding, mu2 equals to 1.5 as shown in figure. At present, fiber optics is used in telecommunications for propagating signals from one place to another with negligible loss of energy. About 300 signals could be transmitted simultaneously without any interference, whereas an electric wire could transmit only one. This is also used by doctors to visualize internal sides of the body. Thereafter, the duration of sun's visibility. In absence of atmosphere, the sun will be visible for its position from M to E as shown in figure. This is M, this is E on horizon. However, in presence of atmosphere in which mu decreases with height due to the phenomenon of TIR, the sun will become visible even when it is below the horizon. Therefore, angle of incident is greater than the critical angle and will remain visible for some time even when it goes below the horizon as shown in the figure. Here, if you are standing here, you can still observe the sun. Already the sun is below the horizon. This result increases in duration for which the sun is visible. It is estimated that due to this effect, the period of visibility of the sun increases by 2 minutes in the morning and 2 minutes in the evening. Action of poroprism. A right angle isosceles glass prism is called the poroprism. It is used in periscopes and prism binoculars either for bending the rays through 90° or 180°, erecting the images through total internal reflection without any loss of intensity as shown in the figure. In all these situations, angle of incidence 45° is greater than critical angle theta c, which is equals to 42°. Light is propagating from denser to rare medium at the reflecting surface. Now the prism. The prism is a transparent reflecting medium bounded by two plane surfaces inclined at some angles. Generally equatorial, right angle isosceles or right angle prisms are used. In figure, the triangle ABC, here you can say A, B and C, is the principal section of the prism, and the angle BAC is the angle of prism which is denoted by letter A. ABED and ACFD are the two reflecting surfaces. The line AD is the refracting edge and the surface BCEF is the base of the prism, which is usually grounded. In given figure, a monochromatic ray of light OP strikes the face AB and suffers refraction at two faces AB and AC of the prism, and in each refraction it bends towards the base of the prism. In absence of the prism, the incident ray OP would have traveled along OPML. The emergent ray QR appears to be coming along MQR. The angle LMQ, the angle between the incident ray OP produced forward and emergent ray QR produced backward, that is called the angle of deviation. This is also denoted by letter delta. Now the factors that are actually affecting the angle of deviation. The value of angle of deviation or the deviation produced by a prism depends on the following four factors: the angle of incident, the material of the prism, the angle of the prism, and the color or wavelength of light that is used. The angle of incident, how it's affect? It is found experimentally that as the angle of incident increases, first the angle of deviation decreases. So they both are inversely proportional to each other. When one increases, another decreases. When one decreases, another increases. So if the angle of incidence increases, angle of deviation decreases. If the angle of incidence decreases, the angle of deviation increases. For a certain angle of incidence, the angle of deviation is minimum. This position of prism is called the position of minimum deviation with respect to the incident ray. By further increasing the angle of incident, the angle of deviation also increases. The variation of angle of deviation delta with the angle of incident I, shown graphically in the figure, you can see. In the position of minimum deviation of the prism, the angle of incidence is equal to the angle of emergence. Angle I is equals to I2, or you can say I1 equals to I2. And the refracted ray inside the prism travels parallel to base if the prism is equilateral. What is the material of the prism? It is found that for a given angle of incident, the prism with higher refractive index, example flint glass, produces a greater deviation than the prism which has a lower refractive index, example crown glass. What is the angle of prism? It is found that the angle of deviation delta increases with the increase of the angle of prism A. Therefore, delta is directly proportional to A, or A is directly proportional to delta. This condition is actually getting satisfied here. The color or wavelength of light. The refractive index of a given transparent medium is different for light of different colors. It decreases with increase in wavelength of light. So if the light wavelength is increasing, the refractive index will decrease. If the light wavelength is decreasing, the refractive index will increase. That's it. Thus, the refractive index of the material of a prism is greater for violet line than for the red light. Consequently, a given prism deviates the violet light more than the red light because of the refractive index. So here we have finished this part. It is requested to all of you kindly revise the facts and figures that all we have discussed in this lecture. As many times I have told you, it's for your own benefit, because now if you have observed or not, but if you paid attention here, you may observe it, that every fact and figure that we are discussing in one lecture is actually having its further explanation in the next lecture. So if you missing the previous lecture, you won't be able to attend the next lecture in the proper manner. Okay. So with this note, we are going to end this lecture, and thank you.